Hello everyone, I am Sunita from SNS College of Technology, Department of Mathematics. Here we are going to see a lecture series on the topic diagonalization, and in that lecture video series we are going to see quadratic forms and its definition and examples. First, let us see what is quadratic forms. A quadratic form is a homogeneous polynomial of degree 2 where it can be represented by q of x is equal to x transpose ax, where here A is a symmetric matrix and x is a vector. Now let us see one example. Q of x comma y is equal to ax square plus 2bxy plus cy square for a matrix A is equal to a b b c. Since we have considered the matrix as a symmetric matrix, we are going to take this as A, B, B, C. So if we take transpose also, we will get A, B, B, C. Next we are going to see the properties of quadratic form. So here the matrix A is a symmetric matrix, which means A is equal to A transpose. So classified by eigenvalues of A. So here the eigenvalues of the matrix A will be either positive definite, negative definite or indefinite. Here this positive definite means all the three eigenvalues of the matrix will be positive, or if we take a 2 by 2 matrix, then all the two eigenvalues will be positive. Then negative definite means both the eigenvalues are negative. If it means indefinite means one will be positive, another will be negative. In that case we call the matrix we call that eigenvalue to be indefinite type. So here the applications are these quadratic forms are used in stability analysis and optimization. So next is positive definite. So positive definite is q of x is greater than 0 for x not equal to 0, and negative definite means q of x is less than 0 for x not equal to 0. So indefinite means there will be both positive and negative values. Then there is one more category called semi-definite, which can be given by q of x greater than or equal to 0 and q of x less than or equal to 0, which means one eigenvalue will be 0 and another one will be positive. In that case we call that to be a positive semi-definite. If one eigenvalue is 0 and the remaining eigenvalues are negative, then that type of eigenvalues are said to be negative semi-definite. Next let us see a problem. So here we are going to consider q of x comma y equal to 2x square plus 2xy plus 2y. First, this can be converted into matrix form by using a formula. After that, we will be classifying the eigenvalues of A. Next, we convert the quadratic form. So here, after conversion of that equation, we are getting the matrix as 2, 1, 1, 2. As we know that q of xy is equal to x inverse ax. So here the matrix is 2, 1, 1, 2, which is a symmetric matrix, and we are going to find the eigenvalue. So first we are taking the determinant of a minus lambda I. So we are getting determinant of 2 minus lambda 1, 1, 2 minus lambda. Now we are going to find the determinant value by taking cross multiplication, main diagonal minus opposite diagonal. So we have 2 minus lambda the whole square minus 1. On finding 2 minus lambda the whole square, we will have lambda square minus 4 lambda plus 3 equal to 0. So on finding the square root for the equation, lambda square minus 4 lambda plus 3 equal to 0, we get it as lambda minus 1 lambda minus 3. So here these roots can be found by using a method called quadratic forms, or we can use the simplest L division method, like the sum of the roots should be equal to -4 and the product of the roots should be equal to 3. So when we split this 4, we have to get +3. So when we take -3 and -1, we will get -4, and on multiplying that we will get +3. So therefore the factors can be written as lambda minus 1, lambda minus 3 equal to 0. Therefore we get this. Therefore we get the lambda values to be equal to 1, 3. So since both the eigenvalues are positive, we call Q of x comma y is a positive definite. Next, interpretation. So since Q of x comma y is greater than 0, for x comma y not equal to 0, the graph will be paraboloid. Next is applications. So optimization, model cost functions, energy minimization. In physics, it is used for vibration and elastic membranes. For engineering, we can use for control systems, structural analysis, and etc. So the references are Kreisig book and B.S. Grewal book. Thank you.